a kind of, it has a long history, but many people have now different versions. Various groups have different versions. Is it all right?
Yeah.
Okay. And yeah. And but a phenomena is certainly, which was originally indicated by us, in some form. It is not only observed, it's one kind of analog computer has been developed using this idea, and that's in the market. It's a very successful one, not yet in India, of course, but I mean, anyway, let me try to give you an idea of what was the original motivation. And it's a kind of computer which could do it in an analog way. These analog computers are no longer in classical computers. They are no longer useful because digital one has, I mean, outperformed them. But you can see in our statistical mechanics classes, most of the time we go for, instead of series calculations, we go for, say, kind of Monte Carlo random sampling, and then a computer using this kind of philosophy, analog philosophy, was developed, for which, I mean, at least in chemistry, applications in chemistry has fetched Nobel Prize, but the original authors in classical computing, the simulated annealing, Chakraborty et al. Didn't get yet. The idea was like this. Think of a ferromagnet, or you can take an antiferromagnet also. Basically, if you have n spins, say Ising spins, each spin has got 2 states. So for 2 spins, 4 states are possible. 3 spins, I mean 2 to the 3, 8 states will be possible, and this way it will grow. So if you have a kind of Avogadro number of spins, then 2 to that n number of states, and say I try to kind of number them in any way in a configuration space, and I look for the energy of the Ising ferromagnet, say, and you can see that there are, I mean, say at 0 temperature, you know that if it is ferromagnet, all spins up or all spins down have the same energy. Otherwise, any other configuration has got higher energy. Okay, this is very trivial, and of course there is a barrier. If you want to go from here to here, this picture remains fine, I mean valid even at finite temperature. Only thing, instead of energy, it will become free energy. Yeah, sorry, I mean it is free energy. And the barrier is, I mean, if you want to go from one ground state to the another, then there is a barrier which is of the order of n, and that may create a problem at any finite temperature to cross over, and that is the reason, unless it is a nanomagnet or something, you will not see the polarity changing in a finite time or in your lifetime. But that doesn't really make any problem for thermodynamics, because these states are all, these are mirror states of these one. So basically you can do thermodynamics very easily. Just one simple point you should note, that if I want to find out, I mean any graduate students when just joins, and if you ask them to find the ground state, they do not scan all the 2 to the n states to find the ground state. What they do, and that is possible, suppose, I mean, imagine just one kind of bowl-like structure here. So any point you start, think of a kind of rolling marble with some kind of dissipation. So what it will do is it will find very easily this, or simulation-wise, it is very simple. You start from here, find any other configuration which has lower energy, accept that, because you have an algorithm to find out the energy of any configuration. So you do not have to roll along all the states, which may be of the order of 2 to the n number of states here. You don't have to roll over all these states. You can jump from one to another. If you find its energy is lower, accept it. If you find and jump here, if you find it has still lower, accept it. Then if you find a jump has taken here, energy has increased, don't accept it. So very soon you will be here, and that's not really even n-dependent number of states. You can make it n-independent number. Forget about 2 to the n search, which is exponential in n. Basically, in a n to the 0 number of steps, you can actually come and find the ground state. That's a remarkable thing which you do not realize. An analog way of finding a kind of optimal value of a function, which may be a free energy or energy, would be searched in an n size problem, which has each unit has got, say, 2 or finite number of states, which means exponentially large number of states. We do not have to search over them, and in n to the 0 time, I can find the ground state or a kind of solution of the problem. This kind of system, yes, this kind of system, I mean, Landau had a scenario that, I mean, if you try to find out the order parameter, which kind of indicates the thermodynamic state of the system, and for a finite system, you will have a kind of distribution like this. The idea is that as the distribution you may have due to fluctuation, it may not always go to the ground state, but as you increase n, this will become thinner and thinner, and the height will increase. So eventually it will become a delta function, and you will have an unique order parameter, and that's the description of the system. There were many systems. The most kind of intriguing and simple looking one, I mean, there are mathematical systems like traveling salesman's problem, Hoffield's model of the brain networks, associative memory problems, all could be could have a similar feature. These could be memory states in our brain, which we learned during our childhood. A child develops its attractors near this. But anyway, let us go to, instead of ferromagnet, a spin glass, where interactions are not always commensurate with each other. What will happen is that there are many solutions which will no one will give this much of minima, because not every interaction can be satisfied, but there are optimal and degenerate solutions. So eventually, if you have a spin, this is the Sherrington-Kirkpatrick model, which is a long-range interaction, but the interactions are, I mean, it has a Gaussian distribution of interaction strength, and interactions can be positive and negative. Gaussian means zero mean. That kind of system will have a zero temperature energy landscape or free energy landscape at any finite temperature, generically looking like this. There would be, of course, it will be rugged, and there would be some barriers. Now, how many of these barriers? Now, many barriers will be of the order of n, and that means, for example, there are spin configurations. Some modifications, 1 or 2 spins changed, will bring me here, and then maybe a few spins to go to another. There would be a barrier which I have to overcome to go to this one, but that would be still a finite number of, if this barrier height is finite. Then say 10 spins I have to flip to go to this, and then after that maybe 2-3 spins, even single spins will take me here, and so on. The problem is, suppose I have started kind of randomly somewhere here, because it's a huge space, and I have started here. The ground state is here. Now I am on this well. Now you can, imagine that this kind of algorithm, that if you find lower, you accept it. If you find higher, don't accept it. Then it will be a problem, because after coming here, if you are here, it is fine. But then how to go there? And then finally, you have to go here, because in between there can be. That means This is also in traveling salesman's problem. Sometimes just a local change in the tour will not make anything. You have to have a global view of where are the other cities and how to. So you have to modify your tour not just locally, but a huge change, and that would be of the order of n change. Similarly, spin configurations, just a few spins locally flipped will not give you from here to here. In between, you have to make huge number of spins flipping, and that will make a barrier of the order of n. Now, the problem compared to here, I mean, science problem, is that this side is not related to related to the other side by any symmetry, unlike here, where everything was symmetrically done. Here I have to do the thermodynamics and this thing. Now somehow if the system is at low temperature, of course you can easily imagine the system will not be able to see and will not be able to anneal there. And so I will be locked into a part of the configuration space, or it will become. Now in case this is really macroscopic, which was proved by say middle of 70s or last century, it was clear that in spin glasses there is no hope of looking for a Landau-like scenario. And well, somewhat later Parisi came with a brilliant idea about some altimetricity of the landscape was, as geometry of the landscape was assumed, and that gave this. And he found that assuming that order parameter distribution is now like this, that it doesn't go to 0 anywhere, and all values are possible, but only there is a most probable value, which will be most likely what you will end up. But this is not a finite, this is a finite n scenario. This is an n going to infinity scenario. Actually, this is only when n goes to infinity, you will end up with a, n means number of components in the system. And you will end up with this kind of system, which will be non-ergodic. And so this is not, because this part of the configuration space is separated from this, because in between a huge barrier is there. A technique, now the computer scientists who are thinking of analog way of doing it found it found it hopeless. And then Kirkpatrick had a, by 80s, Kirkpatrick, the SK model was proposed by Sherrington and Kirkpatrick. Kirkpatrick, by 80s, kind of proposed a kind of marvelous idea. That to go to, of course, in real magnet, probably you have temperature to anneal, but even if it is a kind of map system like traveling salesman's problem, or any other optimization problem, multivariable optimization problem, you will have this kind of problem. So what you do is that you modify your configurations wherever you start from a very lousy configuration so that you can see the, okay, I will come to the annealing problem later. So what their suggestion was is that you start from anywhere so that you can see the entire landscape. Then if your modification of the configuration changes the energy towards, or energy or whatever thing, whatever quantity you are trying to optimize, if that decreases, accept it. But if it increases, don't throw it away, like in nature. Accept it with a Boltzmann probability kind of thing, where instead of temperature, you have a kind of noise factor, allow a noise factor, very large, so that it can accept anything to see the entire landscape, and then reduce the temperature, anneal that noise factor slowly, so that when you are here, still the temperature is finite, or the noise factor is finite, so a huge fluctuation is still being allowed, and you will be probably eventually here. Now, the idea is how much time will take as a function of n. This was being tried because most important is not ferromagnet, but the SK model, which has a mapping to almost all major what was called NP hard computational problem, non-deterministic polynomial. That means problems. That means a problem where any algorithm to search for the minimum is not bounded by any polynomial. Because if it is exponential search, of course you can easily imagine exponential search, of course, but with 100 spins our all computers will be exhausted, and our age is, within our lifetime we will not achieve it. So, and forget about Avogadro number. The idea was, with this kind of annealing, which is a 5,000-year-old technique, and artificial way, a simulated way of annealing, in any such problem would probably help us to get out of these big barriers and then come here. But it was soon clear that no, this is not possible because the barriers are truly infinite. And after Parisi's scenario, Parisi's solution, when incidentally, when Parisi gave this picture solution, if people tried to check with this and find the free energy, and the free energy didn't have all the trouble of this Sherrington quadratic solution, and also the energy obtained, free energy obtained was the minimum. So assuming this kind of thing, which was a conjecture at that time and still remains so, essentially that we have now very good arguments to support this, and it was clear that that means these barriers are truly independent and they will make the system intractable for any such practical annealing business. Now at this stage, it was by mid-80s, it was clear and established that this thing, which, as I said, the simulated annealing technique by Kirkpatrick, applications in many places. For all major design, computer-aided design problems, simulated annealing, this protein conformations, the lowest energy conformations, and so on. Search of these follows Kirkpatrick's simulated annealing technique, and as I said, Potter and others got Nobel Prize about 10 years back for applying the technique and showing that this is working. But anyway, but it was clear that's only for finite systems. For truly thermodynamic limit, this will never work because this is n independent. Now here there was a very, very simple kind of proposal which we made in '89. And this is nothing beyond our MSc classes. In MSc classes we teach, first we were taught and then we teach that if you have a barrier like this, and if the particle is classical, its kinetic energy, random kinetic energy, say thermally, you can get out of this. The probability of getting out of a barrier is exponential. Boolean probability, you have to give this, and temperature is a measure of the kinetic energy in this system, and this will be exponential. And if this barrier is n order, as I said, then it will take this is the probability to get out. That means time to get out is exponentially in n. So that doesn't work. 5 more minutes only. Okay. Okay. Then okay, but still let me finish it. And then think of this as a quantum particle. Now, if it is a quantum particle, the energy will be given by a. You have to give a kinetic energy, which can be done in the magnetic system by a transverse field. So that, and you can imagine that this wave function will get attenuated because its energy is, kinetic energy is lower than the potential energy. So in between the wave functions, did I write somewhere? Okay, no. Okay, fine. But anyway, it is this, but this kappa will become imaginary here, so that means it will become a exponentially decaying one. And then again, if it is not 0 already, there will be this, with this amplitude, it will just go on. So what is the tunneling probability? Tunneling probability is this by this, and that is precisely given by the width and the root over of energy minus potential. Assume now these two are more or less same, and you have a barrier of n. Now you can see that it is square root of n, because potential comes on a square root, because this is just the momentum equivalent, which is the damping factor is V minus E, because it has become negative here. Kappa has become, kappa square has become negative here, because E is less than V. So it has V minus E, minus of that, minus has gone to I, and so it has made it this. So this is the kappa, and kappa is square root of n order, and the minus of this is 1 minus the original kinetic energy term. And in case, and then there is a width. In case the width doesn't depend on n, you have at least an achievement that from exponential of square root or exponential of n time, because this is the probability, so time required will be, escape time would be proportional to e to the n by t. Here t is the energy and here it is gamma, but the exponential of square root of n times the width of the barrier, and in case the width of the barrier goes to 0, like delta functions, you have just this, and even that, anything width goes as 1 upon square root of n would already make it n independent. So there is a major possibility that escape time would be n independent, although classically you cannot. Even a delta function barrier is thermodynamic, because classical noise never looks for the width of the barrier. This simple observation led to many controversies, simply because, you see, by that time Anderson got Nobel Prize, and you are showing it only for a particular one well, but there can be many well, and what is the guarantee that these will actually, in a coherent way, this tunneled wave function will actually tunnel through eventually through the whole sample, where there are many barriers at irregular spacings and heights. But at least nobody knew that this 5,000-year-old technique of classical annealing would never work if there would be really delta function potentials applicable into the molecules. And probably in that case, quantum mechanics would have been discovered earlier, because the classical annealing technique was discovered much, much earlier. Anyway, you do not have time, so I cannot go into this. So what we tried to tell is that this will work, and somehow, okay, last one that we could publish is so far is this. We said that in the phase diagram there is a space where, place where the system is probably ergodic. Around this region is ergodic. This is, and this this is remarkable. A major group from Harvard and other groups not only did computer simulations. These were our things were entirely computer simulation. They did simulations. More importantly, they did major experiment to check these things, confirm these things. They couldn't publish. There are so many other kind of interests going on. Anyway, this, as I couldn't mention properly, that this idea has already been implemented in developing an analog computer, quantum analog computer by a company, where essentially, NASA uses that computer, and they started it, but then there are so many places. Now we tried to show that this will be the real phase diagram. This is the part of the quantum spin glass. It could be, one could go from the glass phase to paraphase by temperature or tunneling field, but very high tunneling field region starting from that line to this green region is probably ergodic, and that means if it is ergodic, because of tunneling possibilities, the barriers can be tunneled through, and then you will have simple annealing, which was classically possible, because once it is ergodic, you can just tunnel through, and then you will have the ground state solutions easily, and that will solve the problem. And we showed some other things which I cannot discuss now. There is a book published maybe 3 months, 4 months earlier, called Quantum Spin Laser Annealing, and that describes or also gives some history of this long story and so many conflicting views fighting each other. But most importantly, there were major experiments by Apley and Rosenbaum, and they also, with Apley, Rosenbaum, Amit, and Uma Divakaran and Amit's student, and then Diptiman, Cambridge also published a book where all the experiments done by Apley and others have been. I mean, actually, Apley and Rosenbaum. Rosenbaum is now in Caltech. He is the president of Caltech now. They did the experiment to check that annealing actually, quantum annealing actually works. The first PRL paper actually acknowledges the entire thing from our paper, but then they published a major breakthrough in science when they didn't, but now they have become our friend, and we published a Cambridge book last year. And this is now from a Japanese group, and this is mostly theoretical. Yes. So I think I have essentially finished. I cannot make it some 40 years of history and also some personal involvement to squeeze within some 30 minutes or so. So, but anyway, I tried to convey whatever was possible.